Welcome back, dude bros. My name is Chili, and this is lesson 5 of the Advanced Game Programming Tutorial series. And today we are gonna answer the age-old question of what is the matrix. Yes, I went there. I went for the easy joke, and I am not ashamed. I have no shame. I know no shame. My name is Chili. So before we answer the question of what is the matrix, first, it's good to, in any situation, it's always good to know why. Why do we even give a shit? Why matrices? Matrices sounds like lots of work. I could be eating pizza pies. Well, I'm going to give you some reasons about why matrices, and then I will say what matrices, and then I will do some stuff. And you will watch me, and if you are diligent, you will follow along. Now, why matrices? Well, first of all, matrices give us a unified representation of transformations, which are the things that we do when we are working with vertices and geometry and stuff. So right now we've got all of our transformations, and they're just all over the place. We've got different functions. We got functions to rotate our vertices. We got operations to translate them and scale them. And we can bring that all into one unified representation under the banner of the matrix. Now, the second reason why you should give a damn, and it's a pretty big one, is hardware uses matrices. It uses them in its internal logic, and it uses them in the application programming interfaces that you use to operate the hardware. So if you don't know matrices, you're fucked. Now, number 3 is, why are matrices a good idea? I mean, unified, that's nice, that's very aesthetic, and hardware is very practical, but why? And one reason is that you can do something with matrices called concatenation, which is basically you can string them all together in one big man train of transformations, and you can compress them all into one single matrix that you only have to apply once to every vertex. Yes. So what does that mean? Well, let me give you an example. A very simple example. We'll use vectors, actually. Let's say you want to get to point A from point A to some point B. If you don't know where point B is, but someone gives you directions, and they say, first, go in this far in this direction, then, hang a right and go this way, and then go in this direction for this far, and then go this way, and then you go this way, and then you go this way. And there you go. And then you'll be at point B, where you want to be. And that's fine. But if you had to calculate this, on a computer, you would have to add 1, 2, 3, 4, 5, 6 vectors together. And if this were a transformation that you had to apply to, say, 10,000 vertices, that's a lot. That's 6 times 10,000, that's 60,000 vector additions. What you could do is you could add all these together once, come up with a single vector, and then just apply this vector to every one of your vertices. And then you would go from 60,000 additions to 10,000, which is a really good savings. Now that works fine, but you can't do that with vectors and rotation. Vectors just simply can't store enough information. They're not big enough. You need a bigger matrix. And if you have a bigger matrix, then you can take a bunch of different rotations and lump them all together into one single matrix, just like we did with the translations and the vectors there. So let's say you have a robot pincer hand, and it's attached to some kind of crazy articulated arm thing. It's like super articulated. It is the most articulated arm. And that sits on the ground somewhere in the world. So this model has a model space, right? And its vertices are centered around the model space. And here's your world. The base of your arm has a position in world space. And you want to basically translate this whole hand, all the vertices in this hand, from model space into world space. How do you do that? Well, first you offset to the center of your first joint here. And then you rotate around this joint. You rotate the whole hand. And then you offset to the second joint and you rotate. And then you offset to the third joint and then you rotate. And then you offset to the fourth joint and rotate. And then I guess you offset to the base, and if the base you rotate depending on where the base is facing, and then you offset to the position of the base in the world. And that is how you would end up with the final translation of your hand vertices in your robotic arm. And again, if you have like 10,000 vertices in that robot hand, then that's what? 1, 2, 3, 4, 5 rotations plus 1, 2, 3, 4, 5, 6 translations that you have to apply to every single vertex in that hand. But what if I could tell you that you could just cram all of these operations into a single matrix and then apply that matrix to the vertices in the hand and save yourself a whole shit ton of repeated operations and rotations and stuff, because that is exactly what you can do, and it is pretty good. So this is why matrices. Now, what are matrices? Let me get rid of this bullshit. So you've already seen a matrix. You've seen several. I don't want this. I want a new layer. There we go. Let me refresh your memory. Here is a matrix. Now you might say, Chili, I know my vectors, and I know that that is not a matrix. That is a vector. And you would be right and wrong at the same time. It is indeed a vector. But the thing you have to understand is that vectors are matrices in the same way that squares are rectangles. So a vector is just a special case of a matrix. In this case, this vector is a matrix with 2 rows and 1 column. So it's a 2 by 1 matrix, which happens to make it a vector. Here is another vector. This one is a 1 by 3, and it's also a matrix too. Here is a matrix, and it is not a vector. So what makes a matrix a vector? Well, one of the dimensions has to be 1. So it can be an n by 1 or a 1 by n, and that makes it a vector. Also a matrix, but a special matrix, a vector. Whereas a matrix in general has n by m dimensions, n rows, m columns. N and m can be the same, they can be different, as long as they are greater than 0. So, vectors, matrices, you write a matrix just like this. There's tons of ways to write them, but I'm going to write them like this with square brackets. And a lot of people, when they write a variable for the matrix, they use something like a capital bolded letter. Whereas vectors are often written like this with a little arrow on top. Matrices are often written bold and capital. I don't know if I'm going to write the bold so much, but I'll always make a matrix variable a capital. So yeah, that's the representation of a matrix. Now on to the fun stuff, the operations. How do they work? Because that's where the fun really comes in. So let me just undo all my bullshit here. So what operations can you do with a matrix? We'll start with a nice square matrix here. And let's say you want to add another matrix to that one. Well, you can do that. But if you're adding matrices 4, 6, 7, square root of 2, the dimensions have to be the same. Right? This would be 5, 8, 10, and 4 plus root 2. So the dimensions have to be the same. You can't add, like for example, a 2 by 1 vector to a 2 by 2 matrix. That doesn't work. It's the same rules for vectors. Vectors, you got to add the same dimensions together. Can't add a scalar to a vector. Can't add any matrices together which have differing dimensions. It's no good. Won't happen. Don't try it. Next thing you can do with a matrix, you can multiply it by a scalar. And we've already done that for vectors, right? Can you guess how it works? You just multiply all of the elements in the matrix by the scalar. So you get 4, 8, 12, 16. That's the result. So those are the simple operations. Now, we add vectors together a lot. We add matrices together seldom, if ever. It's not a big thing that you have to worry about. Multiplying a matrix by a scalar is something that you do. It is a done thing. And it's very simple, so I'm not going to go over it any more than I already have. Now here is where the interesting shit comes in. We can multiply matrices by each other. So we can take a matrix 2, 3, 4 and another matrix 5, 6, 7, 8 and multiply them together, and that will give us a result matrix. Now how is this going to work? How do you think this is going to work, dudes? Well, you might think that's easy, Chili. I got this one covered. You multiply 1 by 5, you put it in here. You multiply 2 by 6, you put it in here. And no. That is not how it works. Life is not that simple. And if that were the case, matrices would not be interesting. No. Matrix multiplication is far more subtle and intricate. So let's see how we do it. Well, we go by every element in the resultant. So let's start here. Element 1. Right here. How do we get this element? Well, the first matrix, we'll call this the row matrix, and the second one, we'll call this one the column matrix. And how we do it is, let me get my colors here. This is row 1, this is row 2. We'll get blue out here. This is column 1, this is column 2. So element 1 is row 1, column 1. So we take, let's get green. we take row 1 from the first matrix. We take column 1 from the second matrix, and we multiply them together and add. So how do we do that? How do we multiply these rows and columns together and add them? Well, we multiply the first element in the row with the first element in the column. 1 times 5 is 5. We multiply the second one by the second one. 2 times 7 is 14, and we add those together. We get 19. That's the answer for the first one here. Next. Again, row 1, column 2. So, row 1, but this time, column 2, multiply 1 by 6, 6. Multiply 2 by 8, 16. The answer, 22. 22 goes in here. Next, we'll move on to row 2, column 1. So now we're going by row 2 here. 2 by 1. So here's column 1, row 2. 3 times 5, 15. 4 times 7, 28. That's 43. And the very last element is going to be 3 times 6, 18 plus, give it this one here, 4 times 8, 4 times 8, 32. Almost messed it up there. Answer is going to be 50. 5, wait, that was 15, 50, 50. So that is how you do matrix multiplication. Let's, well, you take the rows in the first one, columns in the second one, and you use the row column from the destination to find which row and which column you're going to multiply and add together, and then you do it. And you keep doing it for all the spaces in the destination until you've got a full matrix. Now, I've got some stuff here. I've got some tech. So check this out. Here is a little demo that you can check out if you look on the web page here. And it shows you with this row and column, you can choose the destination position. And then it's going to get you your source, your left hand and your right hand matrices. Let's make them the same size. Oh, that was B's column 3. There we go. Good. So now it's a 3 by 3. And so you can adjust and see how if you're going for this element in the destination, then you're going to get this row from A and this column from B. You're going to multiply them together, add them up, and get your result. And that just happens for every one of the elements in the destination matrix, the result. So you can check this out if you want to fool around with matrix multiplications. And what else? And there's also this one here. You can multiply one matrix, or wait, multiply two matrices. So let's pick, let's go for a 2 by 2. Okay, second matrix. And you're stepping through it, you're multiplying 0 by 3. Then you're multiplying this one by this one, you get 4. You keep going along here, you step through it. Shows you how it works. Just a couple little interactive demonstrations of matrix multiplication for you. Now, you can't multiply just any two old matrices together. Let me see here. Gotta get rid of this one. There are rules to follow. Like imagine trying to multiply together 1, 2, 3. These two matrices, which are actually vectors. 2, 4, 6. I mean, how's that going to work? Because you got to go down. Scratch that. You got to go across this one and down here. So you can go down by 3. But I mean, let's say you go for your in your matrix, you go for your first element here. It's 1, 1. So you go in the first row, down the first column. You go, well, 1 times 2 plus, and your next one you're going to go, what? Something times 4. But you can't go across to the next column in here because there's nothing here. You can go down, but you can't go across. The dimensions don't match up. So how do we match up dimensions? Well, let me tell you something. You know already we can multiply two matrices together if they're square and they have the same dimensions, because we just did it. Like 2, 3, 4, 5, 6, 7, 8, 9 times 0, 0, 1, 1, 0, 0, 0, 1, 0. I don't know. This you could do fine. That's no problem. But what you don't know is the dimensions don't have to be the same. That's no problem. For example, I'm going to give you a 2-dimensional matrix here. I'll give you 1, 2, 3, 4 times 5, 6. This works fine. And the result is going to be the same kind of vector as this one. It's going to be a 2 by 1 vector. And it works because, I mean, look at this one. You go first element, first row, first column, second element, second row, first column. They all match up. 1 times 5 plus 2 times 6 is 11. And 3 times 5 plus 4 times 6 is 15 plus 24, which is 39, I'm going to say. Yeah. So that works fine. And interestingly enough, you get the same thing in as you get out. You multiply square matrix by a vector, and you get the same kind of vector out again. So the rules are very simple. This matrix is 2 by 2. This vector is 2 by 1, and the result is 2 by 1. Here's the rule, guys. It's very simple. To be able to multiply two matrices together, these inner dimensions have to match. So the number of columns in the first one has to match the number of rows in the second one. And the two outer dimensions just give us our result matrix. So the number of rows in the first one and the number of columns in the second one gives us the rows and columns of the destination, the result matrix. So there you have it. You make as long as the inner dimensions match, you can multiply those motherfuckers together until the cows come home. And the outer dimensions will determine the size of the result. So for example, let me just get rid of that. One, 2, 3, 2, 3, 1. Yeah. So what? Let's make this a little exercise. What dimension would you expect for the result? Well, this one has 1 row, 3 columns. This one has 3 rows, 1 column. So we know that we can multiply them together. And the result is going to be 1 by 1. So just a scalar. Just a single scalar. You multiply a row vector by a column vector, and you get a scalar. Which is interesting, but we won't be doing very much of that. And so on. I'm not going to bore you with all the details, all the different scenarios. The main thing that we're going to do is we're going to have vector, maybe it has 3 elements or 4 elements, and multiply in front of that a square vector which matches the dimensions. So like this. That's the main situation that we're going to see. And the answer will be another vector representing a position in space that we can use. Alright. Now you're not restricted, of course, to writing just plain numbers inside these vectors. You can write a vector like x, or a matrix like x, y, z, w or something. And a vector like sine theta, cos theta, or whatever is equal to something. I don't know. That's all perfectly fine. And so let's do that and demonstrate something very useful. So we know how the vectors work, how matrix multiplication works. I hope so. If you don't get it yet, then go on the net and read some shit up, because you're going to need to know matrix multiplication fairly intimately. So we know we can multiply matrices together by some combination of adding and multiplying their respective elements. But why? Why is this operation useful to us? Well, let's take a look here. Let's take a little look-see. I'm going to make a little matrix for you. And the elements are going to be cos theta, negative sine theta, sine theta, and cos theta. And this one is going to be x and y. So the vector v is equal to this matrix times this vector. So what does that equal? Well, let's work it out. We know it's going to be, I'm just going to write it like this. Make it big. No, it's not big enough. I'll make it bigger. Make it smaller and bigger. Right like this. Well, we know that this is a 2 by 2. And this is a 2 by 1. So we're expecting a 2 by 1 here. 2 rows, 1 column. So what is the value of the rows and the columns? Well, x times cos theta plus negative y times negative sine theta, which is negative y sine theta. And now we have x sine theta plus y cos theta, which is equal to v, which is equal to vx, vy. So x is equal to this, y is equal to this. Does this look familiar to you? I hope it does, because we just covered this. And the answer is it's just our old friend, the rotation formula. X primed is equal to x cos theta minus y sine theta. And y primed, well, you can't read this. because it's off the screen. So let's just I can't read it. I can't find, there it is. And y primed is equal to x sine theta plus y cos theta. So this is actually just our old friend, the rotation translation. If we create a matrix with these values of sine and cos in the elements and multiply it with any vector, we're going to get the rotated form of that vector, rotated by theta. So this, my friends, is rotation vector. No, rotation matrix. So what else can we do? Well, let's create a new matrix. We'll write here k and k in the diagonal, and x and y. And the result is going to be k times x plus 0 times y, which is kx, and 0 times x plus k times y, ky. This is just the same as scaling x and y by k. So here is, now let's just write this here, rotation, scaling. Here are our rotation and scaling matrices. By the way, I just want to let you know, if you write a matrix like this, with 1 and 1 here, and you multiply any vertex, or any vector, by this matrix, the result will be the same as the original vector. This matrix will not change a vector if it's multiplied with it. So we call this one the identity matrix. It'll be useful later on. So we got our rotation and our scaling transformation. Now we have one more transformation that we like to use, and it is called translation, moving stuff around, sliding it around on the screen. And that one, unfortunately, we cannot encode in 2 dimensions with a 2x2 matrix. It doesn't work. So what we need to do, let me just get a new layer here, is we actually need to add another dimension to our what should I call it? Dx and dy. So what we do is we extend our transformation matrix an extra dimension. So now it's now 3 by 3. Now, in order for it to be able to multiply with our vector, we can't multiply it with a 2 by 1 because the inner dimensions wouldn't match. So we have to extend it to 3 by 1. And we just put a 1 in here to make sure everything adds up in the end. And if we multiply these together, we're going to get x times 1, 0 times y, so x plus 0, which is just x, and then dx times 1, so x plus dx, and here we're going to get 0 times x, 1 times y, and dy times 1. Here we're going to get 0 times x, 0 times y, and 1 times 1. So if we extend our dimensions, then we can get a translation matrix. And we put the dx and the dy of the translation in here. So this is translation. My dyslexia is acting up. I'm just joking, I don't have dyslexia. That is a insensitive joke for the people who actually do have it. I just have the thing where I can't speak and do shit at the same time. So, yeah. So by extending our dimensions by 1, we can do this. Now you might think, Chili, that is a lot of extra overhead just to be able to add translation. And that's true, but we're going to do it anyways. And the reason why is, especially in 3D graphics, in 3D, you're going to have matrices like this. 1, 1, 1, 0, 0, 0. Dx, dy, dz. And then here you're going to have like x, y, z, and w. Now w, and there's going to be some stuff in here, I'm not really sure. I have to look it up later. But basically this 1 here in our 2 dimensions is going to be very useful in 3 dimensions, this extra dimension for projecting onto the screen. So we're not going to use it too much in 2-dimensional space, but in 3-dimensional it'll become very useful. This is called, if you use x, y, z, w, it's called homogeneous coordinates, and it's good shit. So we're going to use it in 2 dimensions anyways, just to get you guys, I don't know, accustomed to the extra dimension. Even though it's only 2 dimensions, we'll have 3-dimensional vectors, but we won't. But it's confusing. You'll see. Anyways, here's how you do translations with vector multiplication. You extend by 1 dimension, and then you put the shit in here. And here you just put a standard non-scaling kind of thing. Stuff that does stuff. Enough chat, more hat. So that is, let me consult my notes here, like I'm all professional and stuff. Yeah, that's all of the translations that we need. Rotation, scaling, and translation. Now the thing is, we've got to actually get this shit into code. So here comes the fun part. Here comes the choo-choo train. Let's go to the project and let's add a new item. Here comes a new challenger. We want to add a header file. We're going to call this one, I could call it mate. I'm going to call it mate 3. So we got a new one called mate 3. We're going to # include. What do we want to put in here? We're going to include vec2. And we're going to include nothing else. Just vec2 for now. So I'm going to make this thing. I'm going to make it a template, just like we did before. So let me just make sure I know how to do this. I'm just going to copy this here. Go back, paste that there. We'll say that this one is underscore mate 3. It's got a type name on it and everything. So this will let us have matrices of floats or doubles or ints if we wanted. Now here's the interesting thing. How are we gonna represent the data? We have choices here. We've got decisions to make, people. We're gonna represent 3 by 3 matrix means we're gonna need 9 elements. Right? Now here's the deal. We could represent this in a number of ways. We could do new and delete with the 9 elements. And that would be good for a number of reasons. If we had a pointer to the heap, so we would call this I don't know, p elements is equal to new new array of elements. If we had it this way, then it would be very nice for moving elements from one matrix to another, moving the contents, because we could use our our std move and just copy the pointers over. Very nice. But the problem with that is every time we create a new matrix, we have to allocate on the stack. And every time we get rid of one, we have to delete, not on the stack, on the heap. And that is going to be a little bit of overhead. I don't like that idea, actually. So scratch the pointer. Now I could create an array of 9, but we're not going to do that either. We're going to do something that I very seldom do, and that's going to be, we're going to create a multi-dimensional array, 3 by 3 array of elements. It's actually, there's no such thing as a multi-dimensional array in C. It's just an array of arrays, but same idea. Now the reason I usually don't do this is that when you're making multi-dimensional arrays, you basically need to know the dimensions at the compile time. I mean, you can fudge one of the dimensions, but you have to know at least one, and I don't like that. I like keeping it dynamic. So I usually just allocate, like a buffer or an array of length times width, and then I calculate the position myself using multiplication and division, or not multiplication and adding, which you've seen this a million times. It's just y times width plus height, right? That was dumb. Y times width plus x. There we go. That's what I always do, but in this case, the width and the height are always going to be 3 by 3, so why not use the built-in arrays and stuff? Multi-dimensional array type notation. Won't hurt anything. It'll make the code nice. By the way, sometimes people think, oh, I had a lisp there. Sometimes people think that addressing an array like this is faster, right? Like, for example, you could have A 9. So let's say you have int A9, right? And then if you want to get at, it's a 2-dimensional array, so you'd have to go, let's say you want to set one of the elements to 1. So you'd go A at y times 3 plus x is equal to 1. And then you've got another situation where it's like int b 3 b at y x equal to 1. So people look at this and say, well, here you've got to multiply and add, whereas here you don't have to. So this one's probably going to be faster. And that is not the case, because what happens is the compiler just takes this and turns it into this. So it's all the same thing. And in memory, this is exactly the same as this. So there's really no difference between these two here. It's just a difference in syntax. That being said, I like this syntax when I can get it and I don't have to sacrifice anything for it. So I'm going to use it. Now, the question is, how is this, which one of these is the row, which one is the column, and how is it laid out in memory? And I often get confused in that situation because I don't use them that often. So I refer to something. I usually just go do a Google image search and just look for an image that shows me how it works in memory. Now this is telling us that in memory it's going to go in this order: 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And in terms of what do we call those things? Subscripts, indexes into the array. They increment by row column. So you go 0, 1, 0, 0, 0, 1, 0, 2, 0, 3. So it's nice just to give myself a little reminder here when I'm writing algorithms. Row column. And it's column row major, I think is the name of it. Column, it goes column first, then row. So first column, second column, third column in memory. No, first row, second row, third row. Yeah. Man, rows and columns mess me up. Anyways, so that is how we're going to store our data. Now we need operations. So, what do we got? Matrix. So here's just a default empty constructor. I don't think I need it. I don't know what constructors I need actually. I think if I define no constructors, I'll still be able to initialize it with an initializer list because it has as its memory, as its data, just a simple array. So I think that's how it works. But I'm not sure. So we need anyways, we need to start defining operations here. So let's get our very simple ones out of the way. We'll go underscore mate3 ampersand operator equals constant underscore mate3 ampersand right hand side. And how we do this is we go we'll do this, there's a bunch of ways we could do it. I'm just going to go memcopy. Might not be the fastest actually in this case, but we're going to do it anyways. So we go, wait, what is memcopy? Why is it not giving me my IntelliSense? What do I have to do to get memcopy? Yeah? How's that? Still can't do it. Now I'm getting pissed off because I don't know what I'm doing here. Windows.h. This is retarded. This, my friends, is what we call an outrage. Okay, I got it now. I still don't think I should have to include Windows in here. That's retarded. Let's look it up. Mem copy. Where is it? C string. Yeah, I don't recall having to include C string. String.h, but I'm going to do it anyways. Okay, memcopy. Let's get on with it. Destination is going to be elements. Source is going to be right-hand side dot elements. And size t is going to be size of elements. Then we return a pointer to this, right? Because the equal operator returns a reference to the object, so you can chain together a bunch of operations if you want to. What else? The assignment operator, I should say, not the equal operator. What else do we want to do with matrices? Well, adding is a thing you can do, but we're not going to implement it because I don't have any use for it right now. So what I'm going to do is I'm going to look at my cheat sheet, which is my project that I have already. And that will save me time humming and hawing on the video, which will save you guys time. Oh, not supposed to look at it. It's a secret. It's a secret. All right, so we need to multiply. I guess let's start with the easy ones. We're going to do underscore matrix mate3. And we're going to do ampersand operator times and equals const underscore mate3 ampersand right hand side. And how that works is we return, we go for each. This is interesting because this is something that we haven't used before, but you can use a for each and iterate through each of the elements in a collection or in an array if the array has a constant size. So I mean, if the array is allocated dynamically, you can't use a for each, but this one is statically allocated, so we can use it. And loud siren noises, thank you very much. Just what I wanted. So for each, and we'll get a reference to for each element E in elements. Now we're not gonna, this one's not gonna be matrix actually, it's gonna be float right hand side. So we're gonna multiply a float. So this is just scalar multiplication. It's not gonna be a float, it's gonna be a T. There we go. So it's just our good old friend scalar multiplication. And we'll just do E times and equals right hand side. And then return this. So this one just multiplies the right hand side, the scalar, by every element in our vector. And this for each loop just gives us a very easy way to go through every one of our elements. Yeah, I don't know which one is better now. You can also write that for each loop like this. It's a ranged based for loop. And then it's the same thing, right? It's just give us a reference to every T in elements. And for every one of those, we do this. So yeah, I want to write it this way. It's faster. You see, in the code I wrote before, it's actually written like this for each float and in element. I don't know if that's like I don't know. I just don't know. But I know that this is standard, so I'm going to use it this way. And we'll see. So we got a little range-based for loop going on here. Very nice. I don't use them too often, but it's nice when you get them. So there's multiply and assign. And here, operator, we'll get our standard multiply. Constant T right hand side. This is a constant method because it doesn't modify. And we just go, what do we go? We go underscore mate3 result is equal to this. So we copy this into the result, and then we return result times and equals right hand side. And there is our standard multiply. This one returns a new matrix, and this one just mutates the current matrix. So there's our scalar multiplication implemented. Now for the fun part, matrix multiplication. So let's just get on with it. Mate3 3 operator times mate3 and RHS constant. Okay, so we got to get the result first of all. Underscore mate3 result. Now for int j is equal to 0 as long as j is less than 3, j plus plus. For int k is equal to 0 as long as k is less than 3, k plus plus. So what we're going to do, let me get my Photoshop up. We got two 3x3 matrices here. One, two, three, 1, 2, 3. And multiply them together, and that will give us another 3x3 matrix. So here is the j's. Here are the k's. J represents rows, k is columns. That's easy to remember, right? K for column. That's how you spell it, right? So we loop through all of the rows and columns in the result. And for every one of those row column pairs, we have to do another loop. Because, for example, in this row column pair of J0, K0, we've got to multiply this row by this column. So 1, 2, 3, 1, 2, 3 multiplications. So how we do that is, first we get a t sum that will hold our running total, and 0.0. And then we go for int I is equal to 0 as long as I is less than 3, I plus plus, and then we sum element I k times right hand side dot elements j I. Now this is the tricky part, right? Now we know that when we're doing the multiplication and adding of a particular row, we're going to loop through the columns in the first one, the rows in the second one. Ah, right. I did things backwards in my original. Okay. This is going to be, this is not going to be good. All right, so JK is fine. So I think we want K I J maybe. we're looping through columns in the first one, rows in the second one. I think maybe these two have to be, yeah, this one should be J here, because J is the row in the result, and K is the column in the result. Right. And so the column in the result comes from here, and the row in the result comes from here. So we want to keep the row constant throughout this inner loop. This is row constant, this is column constant, and these ones are changing. So this should be what we want. And once we've added it all together, then result.elements at JK is equal to sum. And at the end of this, we return our result. And yeah, that's it. Now we need one underscore mate3 operator times and equals const mate3 right hand side. So now we need the mutator, which is just going to be return this equal to and this, fuck that, times right hand side. Now one thing you might pick up on if you're really sharp is in this one we put the meat of the multiplication in the assignment operator, the mutator, and then in the non-mutator we just call the mutator. We create a new result matrix and we call the mutator operation on it. But in this one the meat is in the non-mutator. And the reason for that is for multiplication, you can operate directly on the this, right? You can operate on, this is hard to explain, on the this. You can operate on this object. But with multiplication, you can't operate on this object because you can't be changing shit while you're still doing the matrix multiplication, or you'll alter the results. Like if I do this times right hand side, and instead of having a result and putting the answers in here, if I just put the answers back into this as I was working, they would change the answers that come after them. So you need to have a separate, where is it? Here it is. You need to have a separate matrix to store the results in while you're working. And therefore, it makes better sense to define the meat of the algorithm in the non-mutating operation, because the non-mutator needs to create a new matrix anyways. And then the mutator will just create a new matrix by means of this operation, and then assign that to this and return a reference to this. Throat's starting to get sore, man. But we're almost done, I think. So we've got all of our multiplication operators. What else do we need? We don't need that, or that. All right, let's see if we can, trying to think of a good way of testing out this bull crap. I guess I could just go into game. We'll go, where's game? There's game.cpp. Yeah, get rid of the framework. And we'll include mate3. Let's just write a quick test here. So we'll go mate, oh wait. We'll go back to mate3 here. Type define, I always get these mixed up. Where's the framework? Vec2. Alright, it's like this. So type define underscore mate3 float mate3. There. And now we go back to game. Wrong one. Last video you couldn't see any of the menus that popped up because of my settings on my recorder, but I fixed it. Sorry about that. If you weren't missing much, I guess. Let's go mate3 m. Now I believe I can initialize it like this. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and it lets me initialize it because the matrix 3 is just built on a standard array. So it lets me do these initializers without having to write any special constructor or anything. I don't know, let's call it B, whatever. So 1, 0, 0, 0, 2, 0, 0, 0, 3. And mate3 C is equal to M times B. All right, let's just debug this. Yeah, let's build it. Okay. So we got a lot. A lot of junk in the trunk here. Let's see what happens when we step over. So C is equal to 1, 4, 9, 4, 10. Okay, 1. That makes sense. 1, 4, 9, 4. I should have made the matrices something that would be easier for me to read the answer, because I'm not sure what the answer exactly should be. I think it should double and then triple. 1, 4, 9. So it's doubling the first column. Wait, no, it's keeping the first column the same, doubling the second, and tripling the third. Yeah. Keeping that column the same, 2 times 5, and then next one should be 12. Ugh, I can't see. Well, it's not letting me see it all, so fuck them. But it looks like the multiplication is working, which is good. So it compiles and it apparently works in our very inadequate test that we just run. So now I'm going to write some very simple functions that will generate matrices that we can use for our transformations. So how should we do this? We'll make static functions. So we'll do static underscore mate3. And first thing we'll do is a rotation matrix. And t theta. So this static function will return a rotation matrix based on the theta that we pass to it. So we'll go constant t cos theta. We'll pre-calculate cos is equal to cos theta, and constant t sine theta is equal to sine theta, and matrix 3 r for rotation is equal to, now here's our matrix that I showed you before, and it's cos theta negative sine theta t 0.0, and then the second row is sine theta cos theta, and again t 0.0, and the third row is just going to be zeros. So no, stop that. 0, 0, 0. No, I think the last one has to be a 1. Let's make sure. Yeah, it's a 1. So there is our rotation matrix, and return R. Now static underscore mate3 scaling float factor. So this one is simpler. Factor, wait. Factor, and then we got again t 0.0. So this one's just diagonal of the scaling. So first row, second row is 0, then factor, get out of the way, and then 0, and then the last row is 0, 0, and then factor. Or maybe it's 0, 0, and just 1. Yeah, it's just 1. Because the last row is not, it's not a thing. All right. And return S. All right. Now the last matrix that we got here is going to be translation. Float. No, wait, we don't want float. Fuck float. T. Give me T. X, well, dx, and T dy. And mate 3. Did I do it here too? I did it here too. Gotta remember to keep my templates and my type defs separate. T for translation is equal to, and again, T So we want 1 for the first one, because we don't want to scale or anything. And then we want t 0.0, and then dx, that's first row, and then we want 0, and then we want 1, and then we want dy, and then we want 0, 0, and then last one is a 1. And that's scaling. I mean, that's translation. And one more matrix, special one. Mate3 identity matrix. That's just a matrix that whatever you multiply with it, the result is the same thing. It's basically the same as 1 in just scalar numbers. And identity matrix, I'm just going to copy and paste it from over here. It's just a diagonal matrix with 1s in the diagonal. So we'll just do that and then return I. And that was a horrible idea. I regret everything. Where's my T's? Here they are. Alright, time to get my T on. If I don't put these things in here, then you'll get a bunch of warnings about converting types and bullshit like that. I don't like it. Alright, so now we have nice little functions to create special matrices that we'll need. And we've got our assignment operators, our multiplying operators. There's some other operators we could use, but that's it for now. Now we need one more operator. This is the one, this is probably the most important one. And that operator is it's gonna be a vec2 type T operator multiply constant vec2 T right hand side constant. So there's our vector multiplication here. Multiplying vector by our matrix. Now here's the thing. Here's the thing, my friends. Remember when I said if we got a 3 by 3, we can't have a 2 by 1 because these don't match? Well, what we're going to do is we're going to multiply a 3 by 3 by a 2 by 1. And we're just going to pretend that there is a 1 in here. Because there's only 2 results in here. So we're just going to fudge the answers so that we're going to do the multiplication as if there were a 1 in this third position. But there's not actually going to be one. So we're not going to do a loop and do proper matrix multiplication. We're going to fudge the answer. So the answer is, of course, now let's just see here. Let's see, I've got A, B, C, D, E, F, G, H, I times X, Y. with a phantom 1 in here? The answer to that is going to be ax plus by plus c times 1, and dx plus ey plus f, and in the phantom answer it's going to be gx plus hy plus I. However, we're going to ignore this here because for all the transformations that we're doing, these are always going to be 0 basically, and this is always going to be 1, so it's not going to be important really. We don't care about them. These aren't the droids you're looking for, is basically what I'm trying to say. So how do we accomplish that? Well, sir, I guess the way to go about this is to go underscore vec2 of type t results dot x is equal to elements row column. So that was going to be 0, 0 times right hand side dot x plus elements 0 row 1 times right hand side dot y plus elements 0 2 dot y is equal to, we can just copy in this one, and this one's just going to be 1 second row and second row, and that's all we're really interested in here. And then return result. So there you have it, my friends. There's how we will represent multiplying a vector by a matrix, which will be equivalent to transforming a vertex, I should say. Now it's time to put them to the test. First we're going to build it, make sure this doesn't puke on us, and it did not. So let's just try a quick little test here. We'll take it for a little test spin. We need to go, I guess, polyclosed. So we have vector, position, angle, scale. And what we're going to do is we're going to go mate3 transformation is equal to mate3 so we want to rotate, scale, and then translate. Doesn't matter what order we rotate and scale in, but translation will affect rotation and scale, so we want to translate last. So we want to rotate by theta, well, that's angle, and we multiply mate3 scaling by scale, and we'll multiply that with mate 3 translation, and translation takes a dx and a dy. Actually, we're going to change that. We'll go to mate 3 here. We'll make it take a underscore vec2. Yeah, sure. Constant underscore vec2 t. Offset, I guess. O. Off. Offset. We could call it ds. Names. I'm just going to call it offset. Translation, and we'll go, instead of dx, we'll go offset.x, and instead of dy, we'll go offset.y. There we go. And now we'll go back, back, back. And now we can use our vertex as it is. We don't have to go into x and y. Very nice. So our transformation matrix is just a concatenation of rotation, scaling, and translation. And now we just do draw line clip trans times I. I plus 1. Trans times I plus 1. My butt's falling asleep here. And vertices dot back dot rotation scale position. Get rid of that. Trans times vertices dot back. Trans times vertices dot front. All right, and that should be that. Mate 3 undeclared. Okay, well, yeah, that's fair enough, I guess. You had me at hello. Okay, mate 3. There we go. Build. Class template has already been defined. Well, I guess I should probably put my pragma once in here to prevent that kind of error. Translation must return a value. That makes sense. Let's do that. You have a point, Mr. Compiler. I find your opinions intriguing and wish to subscribe to your newsletter. And there we go. We did it. We did not it. I did not do it. It seems that we're performing our operations in the wrong order. We are first translating and then rotating. And I don't even want to think about scaling because I think it's going to make things bad. Yeah. See how the scaling is bringing it in here? So the translation is happening at the wrong time. It's effectively doing the translation first, which doesn't make sense to me. Let's go back to Let's go back to polyclosed here. Okay, we're doing rotation, scaling, translation. Let me just make sure I'm doing this right. I might have done it backwards. Nope, we're doing multiply rows by columns, get the thing. Nothing wrong with my ordering here. So it should rotate. It should take this rotation matrix, scale it, then take the result of that, translate it. And that would be the transformation. But instead, it's doing this one first. That won't happen. It almost seems that I have to put my matrices in reverse order. Yep. That's it. Yeah, your good old code 3. I gotcha. So what I have to do is I have to put my translation here, then do rotation, then do scaling. That seems wrong to me, but I'm probably just thinking poorly. Now this should work. Yeah, this works. There we go. That is a little bit strange to me, but I feel it should be the other way around. I feel like you should apply the translation matrix last. And yet that is not the case. Do the translation first. What if I multiply the rotation and the scaling together first? I get the same thing I got before, right? No, now I get... Oh, right. It depends on which one on the right hand. It's not the order. Maybe it is also the order, but it's also the positioning. Because you're applying the translation to it. Like with, okay, maybe I might have this in my head, but think about when you're doing you're multiplying, a 2x2 matrix to a 2x1 vector. You're applying the matrix to the vector. The thing you're applying is on the left side. The thing you're applying it to is on the right side. So it's the same when you're doing translation to some other transformation. You're applying the translation to it. So the translation has to be on the left-hand side. Maybe? I don't know. I'm not exactly sure anymore. I'm not sure about anything. That works. And the scaling works too. What if I were to change the order? So first we apply the translation to the rotation, and then we apply the scaling. Okay, so far so good. That's fine. So apparently it's not so much the order in which you do the operations as the, I mean, not so much the timing, which one goes first, as the positioning, the relative positioning, the left and right relationship of the different operations. Translation should be on the left-hand side. If it's on the right, you're going to have problems. Anyways, this was matrices in all their glorious glory. And I don't know what to say. I mean, you gotta know matrices if you're gonna do 3D graphics sooner or later. Especially if you want to work with the hardware directly. So it was necessary, and it's also really useful, and I think they're kind of cool. So we did it. We did it. Next time, what we're going to do is we're going to work on applying these matrices to the game in a better way. We're going to remake the viewport and camera system, except it's going to be better this time. And we're going to make it to work with transformation matrices. And we're also going to we're going to create a map for the ship to move around in. So we're going to have the map on the screen. The ship will be scrolling over the map, and the map will be clipped to the viewport. And that will set the stage for the next lesson, and in which I'll probably do the physics of the ship actually rebounding off the walls of the map. And that one is going to be fun, let me tell you. There we'll be doing a lot of vector algebra. But that's another story. So next episode we'll be doing scrolling with the camera and the viewport, and vectors and matrices, and we'll be loading a map and displaying it. And my throat is dry. So I hope you enjoyed the video. Hope you understand matrices. If you don't, go back, look at those web pages that I came up with, and check the links, or just search online for matrix multiplication tutorial or interactive or whatever. Because it's important that you know how to do matrix multiplication in programming. It comes up a lot. And yeah, that's about it. So if you liked the video, if it added something to your life, then please click the like button. It helps out a lot. And I will see you guys next tutorial, unless I see you on the forums later.